Okay, let's start. So we're happy to have Siddharth speaking to us today. Siddharth is joined us a bit over a year ago. He's a second generation RAP after completing his PhD with Prala Harsha, who is one of the first RAPs was one of the first RAPs at the TTI. So we're happy to have, I don't know if that's actually the first, I think it's the first, but second generation REP we have here. And Siddharth works on incentives that we'll see today. We'll talking to us about the median treatment effect. Looking forward to the talk.
Yeah.
Thanks.
Thank you, Nari. Welcome everyone. Today we will be learning about median treatment effect estimation and how actually I came about this problem. So I apologize for the title I put up there and what was advertised. There is a change, but to make up for that, I have this slide, or just which probably we'll appreciate it more once we go through the talk. So anyways, let's begin. And let's start with a basic question, the very basic question, which is what, causal inference, a good part of causal inference is about how do we test the efficacy of a drug, right? So suppose you have a cure for procrastination and you want to test it. What are you going to do? Well, you can take the pill on yourself and see, but that's not what we generally do. The gold standard is to use a randomized controlled trial. So what do I mean by this, just to set up? You will enlist some people, some participants in the trial, and you randomly split them into two groups. One group will receive the drug, the treatment, and the other group will be the control or the placebo group. So they will receive sugar pills or something like that. And then you let some time pass, and you compare the number of people who procrastinated, like maybe a week or a month, depending on what your horizon is. And you try to compare this incidence rate, which might give you a measure of how efficient the drug is. But let's try to formalize the setup of a randomized controlled trial. Now, there are a lot of assumptions in the literature, so I'm not going to speak a lot about the assumptions, but assuming reasonable assumptions, which are sort of in this causal inference jargon called work-versus independence, we assume that the n participants actually have presupposed treatment and control values. So what do we mean by that? So if you look at participant 1, if you give them your drug, they would not procrastinate. If you do not give them your drug, they would. So these are values which are presupposed to exist. I'll come to the covariates in a bit. And for participant 2, it's actually the drug is affecting them adversely. Like they would procrastinate if you gave them the drug. Like imagine if your drug involves a large dose of caffeine, they might get agitated, or they might not be able to focus. But otherwise they would have done pretty well. They would have not procrastinated. So these are presupposed to exist, and we discover them by the randomized control trial, right? And the covariates are generally in pieces of information which we believe are helpful in predicting these values. So they could be like age of the participant, maybe what's their gender, stuff like that. So these are some feature vectors. But for this talk, we are going to suppress the dependence of covariates on the actual treatment and control values. Okay. So because we want to give an algorithm which works without assumptions. So I'm going to use boldface to denote vectors, and it's the normal face to denote just scalar values. So A is the treatment vector and B is the control vector. And the task of the experimenter or the designer is to actually discover these values. And in the slide that we saw previously, we are actually splitting the participants into two groups. So we select a subset of n, so a subset of participants at random, and we give them the treatment, and the remaining are the placebo, right? So the red ones are the ones which receive the treatment, and the blue ones are the placebo group. And now you can ask, okay, what is this random way of assigning treatment and control to the different participants? So this depends on the context. The most classical thing is to just do it by tossing fair coins for each participant. It's called the Bernoulli trial. but it can, for instance, be dependent on the covariate information. I don't know. Oh, sorry. Yeah. So you might want to give a partition of the group in such a way that the covariates are balanced, if you assume some kind of influence. But this depends on the context. But this is the way an RCT is generally thought of. So what are the outcomes of a randomized control trial? Once you have assigned some group to be in the treatment and some group to be in the control, you actually end up learning only the treatment values for the treatment group and the control values for the control group. You do not learn the other part of the data. So the potential values of these AIs and BIs are what are typically referred to as potential outcomes in the causal inference literature. For this talk, we will be just assuming binary potential outcomes. That is, either the person procrastinates or they don't. But you could imagine a graded version of that as well. So this is the fundamental challenge which I already alluded to, that you can observe either AI or BI, but not both. So it's kind of like wanting to do statistics with constrained access to the data, right? So I hope this part is clear.
What is BI?
So BI is like the value that participant 1 would get if they were not given the drug.
If they were not given.
Yeah, it's like a counterfactual to the actual thing.
Why you don't consider the opposite case? So BI is in general a variable of AI, right? And you take only one its value. So the control would be also what will happen to this participant if he or she is given the drug.
Right. So the control is also what would happen if they were given the drug. In the actual trial that you ran, you gave them the drug, so you get to observe this value, but you do not observe the value B1. You observe the value A1 but not B1 because you gave them the drug. So if the drug worked on them, you will, let's say that they were actually cured by your drug, so you would fill A1 to B1. But you would not know what B1 is because you did not get the chance to give them the sugar pill. So it's like you can only have constrained access to this table and you want to get some statistical information out of this. So how do we measure the efficacy of a trial? So the most popular estimator is something called the average treatment effect. That is, you just look at an individual and look at the difference in what would happen to them if they were given the treatment versus what would happen to them if they were given the control, and then you just average. This measure is what is typically used, or it's one of the most popular ones for measuring the efficacy of a drug. And this is strictly speaking the sample average treatment effect because it's just the average treatment effect of the people who participated. But for the purposes of the talk, let's just stick to this as the average treatment effect. So tau is just a name given to ATE. It's just called tau in literature. It's just a name.
So it's not ATE of tau. It's ATE, which
Sorry,
is also called tau.
It's just called tau. I did not mean like ATE of tau. I'm sorry. Okay. So just for an example, let's look at this treatment and control vector table. So we have the n participants and these are their treatment and control values.
AI is what will happen if you give the drug, yeah?
Yes.
Oh, sorry. That's what I misunderstood.
Yeah, AI is what happens if you get the drug.
I thought it's a characteristic function that you give the treatment. Oh, never mind.
So in this situation, as you can see, if these were the actual values which we are trying to discover, the A minus B vector is sort of 0 in the top 1/3 and 1 in the middle 1/3 and 0 in the bottom 1/3. So the average treatment effect value is 1/3. So yeah, one thing that would happen is these guidelines would disappear as the slides keep coming. But I would like you to remember this partition, that there is something happening to the top 1/3 of this table and then the middle 1/3 and then the bottom 1/3. So how do we estimate the average treatment effect? So this is a very classical problem and what's used is called the Horowitz-Thompson estimator. Okay. So what it does is a very simple thing. It just says that let's sum up the values of the treatment vectors for every person who receives the treatment and divide it by n/2, and let's subtract the similar quantity for all people who do not receive the treatment. So at least this is something consistent. Once you know your treatment outcome, you can compute tau hat, right? Because yes.
Oh, do you consider the case when AI is smaller than BI?
Yes, we will consider. All possibilities are there.
So when the drug actually hurts you.
Yeah. I think this was sort of there in this for
Oh,
the
yes.
participant too. Okay, so it's sort of not very difficult to convince ourselves that this expected value of this thing, where the randomness is in your design, because you already presupposed the treatment and control values, this will be an unbiased estimator for tau. And that's kind of easy to see, because if you just use linearity of expectation and if you analyze the expectation of this quantity, it would be AI times half, and that n by 2 works out nicely to cancel everything. So this is a very simple estimator to get the average treatment effect, and this has been heavily analyzed. Like I think, I mean, there is just no end to how many papers that are written on this. But you can typically also draw confidence intervals around the error of the estimator by using central limit theorems, and lots of things are known about this. But the question I would like to ask is it enough? Is this single quantity enough to capture what we mean by the effectiveness of a drug? So consider these two cases. Okay, these are two control and treatment vectors, two different control and treatment vectors. On the to your left, the treatment and control vectors to your left have a different makeup than the treatment control vectors to the right, right? Clearly, like if you look at this right hand side, this drug is actually able to adversely affect some part of the population. But if you look at the left hand side, it at least does not affect anybody adversely, right? Some people benefit out of it, some people don't. But the average treatment effect in both cases is 1/3. Right, because if you just like make this computation, it just turns out to be 1/3. And clearly these are two different scenarios. So we need a different measure of efficacy. Average treatment effect by itself doesn't suffice. So yeah, typically this is what is said, that it doesn't capture the heterogeneity of the data fully. So what is another popular way to measure efficacy is called the quantile treatment effect, and that's what we are going to study. So what is the qth quantile treatment effect, right? So imagine a value of q like half. In fact, that is what we would focus on. So we are asking that if you look at this a minus b vector and you sort it, what would be the value at the n by 2th location or the n by 3th location? So like what would be the median in case q is half? And this is what the talk is going to be about. We are going to focus on the case when q is half. So what is the median of the treatment vector a minus b? Right? And since for this talk I have assumed that the potential outcomes are binary, they are either 0 or 1, the median treatment effect has to be a value between -1, 0 and 1. So the median treatment effect is what happens when you set q to be 0.5, and since all entries of the a minus b vector are either -1, 0 or 1, the median treatment effect will also be -1, 0 or 1. It will be one of the three values.
Sorry, can you say again about the motivation to be using quantile?
So in the previous slide, we saw that there are two different scenarios. Clearly, like in scenario 1, nobody is adversely affected by the drug. In scenario 2, 1/3 of the population actually got adversely affected. Yet the average treatment effect in both cases is 1/3. So how do we distinguish these two scenarios? Because if we only use the average treatment effect, we would think that these are the same situations. So there needs to be a measure of heterogeneity of the data. And quantiles are one popular way to bring this out.
Oh, okay. Gotcha. Thank you.
Thanks for the question.
But just when you say distinguish, you don't mean based on observations. You mean like just
Yeah. If this is the only quantity you cared about, how would you distinguish?
But not when you say this, it's not based on observations. This
Yeah.
This is like how you define it based on reality, not based on.
Even the quantile cannot distinguish like 1, 1 and 0, 0.
So even with quantiles, we cannot distinguish all the heterogeneity. That is right, but it is at least somewhat better than the average treatment effect, right? So you are right that there is no way. So this is an impossible problem. We cannot learn the full data or the full table, full treatment and control values if you make reasonable assumptions. Like there are other clinical trials where so there's partial treatment available to you sort of, but we are not assuming all those kind of abilities at the moment. So if we go back to the previous two cases, at least in that case, the median treatment effect does differ between the two scenarios, right? So yeah. Here, in this case, the median treatment effect is actually 0 because 2/3 of the table is filled with zeros. So the median would be 0. And in this case, 2/3 of the table is filled with ones. So the median is actually 1.
So it looks a bit counterintuitive to me because the left table is better than the right table.
Right. So
1/3 of your patients died and it's not good.
yeah, so under that notion, the median treatment effect is just informative. We cannot, like, if we have that the median for one thing is larger than the median for other, we have to be careful about what we sort of infer from that. Since the expected value is the same and the median is larger, that means there would be a part of the population which was really adversely affected.
So that's what you mean when MTE given tau is large, it is bad.
Yes.
Okay, good.
Yeah, like in this case,
Yeah,
1/3
yeah.
of the population
Makes sense,
suffers.
makes sense, makes sense.
Right. So this is already like what is classically being written about. In fact, there is also a Harvard Business School review about which is titled "The Pitfalls of A/B Testing," where they advocate for the use of quantiles and they give various test cases where it would have been better to use quantiles than just the average treatment effect. Right? Yes.
So what is the issue with trying to fix this AT by like reweighting the outcomes? Like instead of 1 minus 1, let's say if I give a more negative weight to the -1 and then take expectation under that.
So you will not get to see A minus B. You will only get to see either AI or BI. You don't know the value of AI minus BI.
Is that not estimable? Like can you not estimate that under some different?
So if you make no assumptions, if you make some covariate based assumption, then it is possible because you can essentially learn the hidden vector, which is explaining the covariates, the relation of the covariates to the actual treatment control values. But if you make no assumptions, or if it's a non-linear situation, which happens a lot in practice, then there is no way to estimate because you can see either A1 or B1, but there is no way to get hold of it.
I'm a bit confused. So far, you're talking about estimation, but in this setting, if we only observe AI and BI, if there's no covariance, then the only numbers we have to work with is the frequency of AI is the frequency of BI. So
yeah, frequency of ones in the two vector in the AI.
those are like those two
Yeah.
numbers are sufficient. And you're saying you can still do better than
We can do something about this problem. And I will go into what is done in the literature and then we will see what we can do about this problem. Yeah, but you're right. This is more or less the data we have to work with if we don't assume covariance. Yes.
So I guess in these tables, like the left column in both tables has the same number of ones, and the right column, like the treatment column, is the same number of ones in both tables, and the control column is the same number of ones in both tables. It's just how they match up,
Right.
right? Which
But we
we don't
can't easily figure out how they match up.
what do you,
we can't.
but I'm a bit confused here because it's so it's not these two are equivalent from my perspective. I can't detect the difference between them no matter what I
No,
do.
you can detect the difference between them because that's what we will see. So if you because you get to see a subset of data at random. See, if you take a subset of data at random from here, in the BIs that you see, I think you will see more. The expected number of BIs will be the same. The expected number of BIs will be the same, but there is a chance that all the values you see are ones. That is, all the people you gave treatment, they all recovered or they did not procrastinate. All the people you gave the sugar pills also gave you a 1. That is, they also did not procrastinate. That is, S happens to be the top 2/3 and N minus S happens to be the bottom 1/3. But in this situation, that's an impossibility. You cannot always see everyone not procrastinating.
Because we can't see all the ones, right?
Yeah, we cannot see all the ones.
But that
It's a very rare possibility, but I'm just illustrating that you can observe a difference.
It's very rare.
Yeah, I guess the question is whether okay, so. And this is because of the finiteness of the population. But if I'm thinking really what I care about is behavior in the population, not on not on 9 people, right? So in the population, I'm not going to be able to see it in the population.
No, so you are right. So what you can think of is that we are quantifying how much you can learn from observations. It's not that you cannot learn anything, but you cannot learn everything, and it's the in between. How much can we can learn the average treatment effect, right, by doing this trial.
Yeah.
Median is a non-linear quantity, but still we can do something about it. It's not that we are trying to. So it's not quite true that we cannot learn the difference between these two situations. There is a small chance we might be able to, but we are not concerned about that. We are concerned about estimating the medians in a sort of good
sample in
manner.
the population.
Sorry?
You're concerned about the sample median or the population median?
So if for the purposes of this talk, this is the population. These n people are the population.
Oh, but then n is huge and okay. So you're claiming even if n is huge, you can still.
No, so I'm not trying to discern between these two scenarios. My aim is to just give you a good estimate for the median. I don't want to discern between these two scenarios.
But you claim you can do that even if n is very large. Okay,
Yeah, we can give an estimate of the median. Some
See the
estimate.
next slide.
Yeah, let's see. Because
Maybe another way of
I'm
saying it is-
probably missing something.
If you look at the number of non-procrastinators and the outcome in both these two situations, the two distributions will have a significant statistical distance.
Right. Yes.
Right.
So, what's done in literature for getting the median treatment effect, right? Let's see that. So, one thing I already said is that since it's not linear in AIs and BIs, it's very challenging to estimate the median. It's not like we can write a Horowitz-Thompson like estimator. There are two main approaches that exist in the literature. One is something what you do if there are covariates, and you assume some kind of linear relationships between the treatment and control vectors and your covariates. So x denotes the covariates, and there's some hidden vector beta and some Gaussian noise, and you just assume A is x beta plus epsilon and B is x alpha plus epsilon, and then it becomes a question about learning these betas and alphas. But since these are linear relations, these are sort of estimable. The question then becomes, okay, how can you do it with lesser variance? And there is a good body of work on the first approach.
So you don't assume anymore
Yeah.
that A and B are Boolean.
So if you want to do the covariate thing, then yeah, I think you have to sort of give up the assumption.
You can take psi.
So but typically they just assume this, and they assume that you get a graded outcome, like you just don't measure whether you procrastinate or not, how much you procrastinate.
So it's you use Boolean values in your talk for simplicity.
Yeah, for simplicity, and I also don't assume covariates. I don't assume any linear relationship with covariates. Another thing to get rid of this covariate problem in situations where a non-linear relationship exists is to just do median of the treatment vector minus median of the control vector. That is, you wanted to do median of A minus B, but you do median A minus median B. That's another popular approach. But I want to again highlight the same example we've been looking at, that these answers are kind of different. So the median of the of the treatment vector is 1, the median of the control vector is 0, and the difference in the medians is 1. But the median of the vector you cared about, A minus B, is actually 0. Right? So these quantities can be different. And in this talk, we are going to focus on the median of A minus B, not median A minus median B. And actually this was the reason I gave the initial title which was advertised, but I don't know why I changed it. So let's try to formalize the setup a little bit more to understand what we can do and what we cannot do. So here's the task at hand. We want to design a way to select a subset of the n people at random. So I've written it can be non-adaptive. What I mean by that is that you can sort of probably assign the first person to a control group, see their outcome, and then decide what to do with the second person. Like in the initial randomized control trial I displayed, it was a one-shot setting. You just assigned some people to treatment and some people to control, but you can do it in an iterative manner. You can assign the first person to treatment or control, see their outcome, and then decide what to do with the second person.
Do you put any restrictions on the depth here? Because
No.
but in practice, you really cannot do it. If you have 1,000 people, you cannot do 1,000 runs. You should go in batches.
Right. So what we will do is we will actually prove lower bounds for non-adaptive algorithms, but the algorithm we give, lower bounds for adaptive algorithms, but the upper bound will be for non-adaptive. Like we'll give a non-adaptive algorithm which will estimate.
I mean the other way, right? I mean adaptive means changing.
Yeah, so our lower bounds, like we will show that median estimation is hard even with adaptivity.
So even when you treat one
Person at a time, it's still hard.
I see.
And this is what, like, you observe the outcomes once you decide which the people who receive the control and the treatment, and you observe the outcomes and you output an estimate for the median. This is the task. And what do we want? We want that no matter what the initial treatment control values were, using the internal randomness in your algorithm, there is a high probability that the estimate you give would be the median treatment effect. Right? This is the, this is one of the first things we would want from a median treatment effect estimate.
Little of n means little of 1, right?
Oh, sorry, yeah, that's a mistake. Yeah, just don't read that.
It's sort of obvious this
So
way.
it wants to go to 1.
Yeah, it should go to 1.
When
n goes to
n goes to infinity.
With n goes to infinity. That is with high probability we want the estimate.
little n of 1.
Yeah.
Sorry for
Yeah,
that. So we can formalize this task, like these non-adaptive designs, in a computational structure which is called the randomized feasible decision tree. So we'll see what it is on the next slide, but it captures all kinds of designs you can think about. So what is a randomized feasible decision tree? Now this slide has really tested my PowerPoint capabilities to add animations, so let's see how it comes out. So you start with a root node, like for any decision tree, and with each root node you have a distribution. It's labeled with a distribution over this set n cross AB. So you should really think of the first coordinate as telling you which person you are talking about, and A or B tells you whether you want to assign that person to control or treatment. Right? A being treatment and B being control. So what the arity from the root is actually indexed by n cross AB cross 0, 1. So for each person that you choose, and whether you choose to assign them control or treatment, and what you observe. So suppose you choose person 1 and you decide to give them treatment, and you observe that A1 is 0. So you will follow that edge out of the decision tree. So once again, this is just to say that. So suppose you sample something from mu, which is an arbitrary distribution. And let's say that you decide to give person I the control group, so BI, and you observe BI then, and you get a 0. So then you will follow the edge where BI is 0. Right? And in this way, you just keep iterating and following this tree all the way down to the leaf of the tree. And the leaf of a tree is labeled with an estimate of the median. That after observing all this data, you want to now say that this is my estimate for the median.
Will it help if the final estimate is a real number between -1 and 1, or it will?
Good, I will come to that. I will come to that. So, this is how we compute, right? We just follow a random path for the input AB. We follow a random path of this RFDT, and we reach a leaf and we output a median estimate. So just to make it clear, these distributions are not dependent on the input, because you have to label the decision tree. Then you compute on using the decision tree on a particular input AB. Right? So, yeah, but let's talk about the fundamental challenge of a randomized control trial, right? That we could not observe A1 and B1 both. So how does that translate to the RFDT? It just becomes a feasibility constraint. That is, along any path in this RFDT, you see either AI or BI, but not both. Now, in the slide, I have written that exactly one appears, but you can imagine a trial where you can sort of discard some people. You don't you don't give them either the control or the treatment. But for this talk, let's just assume that you give everybody something. So exactly one of AI or BI should appear in this tree along any path. And now, yeah, I guess many of you were already alluding to this fact that it should still be very tough to estimate the median. So let's just give a formal reason for that. So consider just two joint distributions over 0, 1 square. So what I mean by this is, imagine a person in your trial and the probability of the different outcomes for that person are given by this matrix. So that person can have a control value to be 0 and treatment value to be 0 with probability 1/3 and so on and so forth. So these are the two different joint distributions over the treatment and control values of a single individual. Right? And you can see that they have the same marginals. One thing to observe is that they have the same marginal. That is, if you just ask what is the probability that this person has A equal to 0, that is their treatment value is 0, it will be 1/3 in the first situation and it will be 1/3 even in the second situation. And it's true. I mean, basically the row marginals are the same and the column marginals are the same. Right? So these are just two joint distributions. And now let's consider two scenarios. Case 1, the data that we are getting, we sample it independently from kappa tensor n. That is, we just make IID samples from this to create our population. So we are trying to prove a lower bound, hence, and we are making a distributional assumption on the data. But the upper bound should work irrespective of any assumptions. This is like a very standard thing, but I'm just clarifying it. So case 1, AI/BI is generated from kappa tensor n, and case 2, AI/BI is generated from eta tensor n, the other distribution, right, and draws from that. So the observation which we'll go to in the next slide is that a randomized feasible decision tree cannot tell apart between these two cases. We will see a reason for that, but roughly it's just because of the feasibility constraint. And because the marginals in both cases are exactly the same, the RFDT can't tell apart which case, is it case 1 or is it case 2. And intuitively, this is the problem with median estimation. Because if you consider case 1, with high probability your median would be 0. Since in a typical sample, these are the frequencies of -1, 0s and 1s. They are respectively 0, 2, n by 3 and n by 3. Right? And in case 2, the median actually with high probability is 1. We have seen typical examples of these two situations already. The examples we saw in the previous slides were all typical for these two distributions. Since the medians are different and there is no way for an RFDT to tell apart between these two cases, you cannot really hope to give a consistent answer for them. Intuitively, that's the problem with median estimation. Let's just illustrate a little bit why is it hard for the RFDT to distinguish these two cases. So these are the two cases, I'll just put them up here for easy reference. And so this was our RFDT and we were computing by selecting a random path. So here assume that the data is generated from kappa tensor n from one of the distributions we talked about previously and it is fed to the RFDT. What would happen in that case? Let's just compute the probability that a given path P is followed by the RFDT, where the randomness is both over the data, the generation of the data, and the randomness in the RFDT, right? So this can just be decomposed as a product over all edges in the path, probability that you choose that edge given that the path before E is chosen. Okay. And let's just focus on a particular edge E, where let's say that edge E is labeled with Bj equal to 0. So if the jth person was assigned to the control and their outcome was 0, then we would follow this edge. So this can be further decomposed as just the probability of choosing the jth person and assigning them to the control under the mu prime distribution, because this node was labeled with mu prime. times the probability that you saw their outcome to be 0. But this is something which depends on kappa. This does not depend on the RFDT. But now you can just replace kappa with eta because the marginals are the same. So this probability wouldn't change. And I mean, this is just making intuitive the thing that we discussed on the previous slide, that an RFDT cannot distinguish between the two cases. And I mean, even if I have lost you, it's just making formal a very intuitive state that we saw on the last slide. So, okay, so now we know that one thing which I did not say is that how does this exactly translate to median or difficulty in median estimation, but a little bit of finesse can sort of make that work. But now since we know that it's impossible to give you a precise estimate of the median with high probability, like in the sense we wanted, what's the next thing we do? We just ask, can we approximately give the median? Right? That's the most natural question to ask. But then we should ask, what does approximately mean? Right? So one thought that comes to us is that we should try to give an additive approximation, maybe, right? Just become additively close to the median. But in this situation, that doesn't quite make a lot of sense. Say I want to be 0.1 additively close to the median treatment effect, then I would know the median treatment effect because there are only 3 possible values, -1, 0 and 1. So we introduce, or rather we come up with a different notion of approximation, which is quantile approximation. So instead of outputting just an estimate of the median, we would output a median estimate and something akin to a confidence parameter. Okay. What do we mean by that? There's a lot of it's symbol heavy, but what I want to say is that think of epsilon as 0.1, then what we are saying is that the median estimate may not be the true median, but it would lie within the 60 to 40% quantile band of the data. Right? That's all we are trying to say. So epsilon tells us how much away from the median we need to move in a quantile sense. Right? So once again, if epsilon is 0.1, what we are claiming is that our estimator or our estimate m hat will be within the 0.6 to 0.4 quantile band, which is a 60 to 40% quantile band of the data. And you can already see that if I just leave it at that, this is a trivial thing to do because you can output whatever you want and just put epsilon to be 0.5. You will always be within the 0 to 1 quantile band. But another constraint we want is this width. Epsilon is what we are calling the approximation width. This should be small. This is a measure of accuracy. You don't want to just output epsilon to be 0.5 because that's just trivial. So this is the notion of approximation that we want for our RFDT.
Doesn't your previous example show you that you can't get this to be smaller than 1/6 or something like that?
You're right. Yeah, this is exactly the next slide. I was just going to
show.
Okay,
I thought you wanted this to go to 0 or something. Okay.
Yeah, I was going to show that there is a limit to how well you can do this as well.
Expectation is taken over all uniform distributions. Uniform distribution of A and B or what?
So the way the expectation here is only over the algorithm or over the RFDT because we want this to happen for all.
Worst case over AT and internal randomness.
Right. Yes. And
I have 10 minutes. So.
I have 10 minutes? Okay.
12 minutes.
Okay. So as Nati already guessed the slide, I can skip through this very quickly, but yeah, sorry for the sudden explosion of information. These are 2 typical samples from kappa and eta, right? From kappa tensor n and eta tensor n, which we have seen many times. But these are the quantile regions of these 2 data sets. So if you look at -1, it only covers the quantile region 0 in this data set, since -1 just doesn't occur. If you look at 0, then it covers the quantile regions from 0 to 2/3. And if you look at 1, it covers the quantile regions from 2/3 to 1. Right? In this. And similarly, you have a different quantile region coverage by -1, 0 and 1 in this situation. Okay? And as Nati pointed out precisely, that since the RFDT can't tell out between the 2 cases, can't separate them, you will be caught in a conundrum. Like there will be, if you output -1 as your median estimate, then you would need a very large width because the data could be coming from kappa tensor n, if the data is coming from kappa tensor n, and I mean you output m hat to be -1, most other times you would require epsilon to be 0.5 for typical samples. And if you output 0, you would cover, it would be a good answer for kappa tensor n because 0 is the median, but it would not be a good answer for eta tensor n where you would need this 1/6. You would need the width to be 1/6. And when m hat is 1, you would again be caught in the same problem and you would need to output the width to be 1/6. And yeah, so there is a bit of subtlety in the way I said it, but this can be finessed into a proper proof that you would need to, with high probability, output a width which is at least 1/6 in expectation. So this is the inapproximability of median treatment effect estimation. But one can ask, is this the worst case situation? Is 1/6 the worst, assuming binary treatment outcomes? What happens if I take KRE outcomes? And how would I compute this for a general situation, right? This is just for the lower bound analysis. What's the algorithm to do that? So yeah, we saw a bunch of impossibility results. So now let's see a simple algorithm. Actually, the impossibility result almost reverses on its head to give an algorithm. There's not a lot we have to do in the binary situation. It's slightly trickier in the KRE situation. So we fix an arbitrary input data a comma the vectors a and b, the control and treatment vectors, and we use a very simple non-adaptive design, the Bernoulli design. So each participant is just put into the control and the trial groups with probability half, and we compute the empirical estimates for the numbers of ones in the two vectors a and b. So just precisely we just measure how many people who were treated actually recovered or did not procrastinate, and you just divide by the appropriate quantities to give you the fraction of number of ones in the two vectors. And let's suppose, just to illustrate how the algorithm would work, suppose rho hat A1. So you estimate that 2/3 of the entries of A are ones, and you estimate that 1/3 of the entries of B are ones, right? Then we know this information. We are sort of convinced that A has 2n/3 ones and B has n/3 ones. What we do not know is how many locations are there which are both ones. That's the thing that we are missing. So what do we do in such situations? So yeah, one thing that we already know is that this fraction, so the rho hat A intersection B, the locations where both things are ones, this fraction has to lie between 0 and 1/3 because it cannot be more than the number of ones in B's. So that we already know is 1/3. And if we can guess what this is, or we basically go over all possible values of this and try to see how much fluctuation happens in the median. It's almost reversing the lower bound on its head in this situation. So for each R, whatever could be our median estimate output, -1, 0 or 1, we compute the width which would cover all values of rho hat A intersection. So just for illustration, so we start with the value 1/3, in which case this is how our data looks. And suppose we want to output 0, R equal to 0. We already saw that this situation is perfectly handled because 0 is the median. But as you vary rho hat A intersection B, you get to 0. And here you will need a width of 1/6 because actually 0 is at the 1/3 quantile. So you would need a width in your approximation of at least 1/6. So you just compute this for every R, and then you output the R comma epsilon pair for which the epsilon is smallest. And this would be your median estimate along with the confidence parameter or the width parameter. And this would have worked for any input A and B. We just sort of instantiated our inputs in a particular way to explain the algorithm. So yeah, if there are any questions, please ask me. This is just like reversing the lower bound on its head, or in other words, as Natty said, you can probably figure out the number of ones in A's, the number of ones in B's, but you cannot figure out the intersection. So you just guess and you go over all possibilities and try to figure out how much the median varies and compute the width which suffices. So this is fine, but now I can sort of illustrate what are our results. So we actually work with KRE outcomes. So typically in a clinical trial or in any drug efficacy trial, you want a graded outcome values. That is 0, half, 1, half denoting that you procrastinated only half the time. So we show that if you have k-array outcomes, this optimal inapproximability width or the optimal approximation width in the worst case situation, meaning for all inputs A and B, in the worst case your optimal approximation width will be 2k minus 3 by 4k minus 2, like some expression, which for k equal to 2 turns out to be 1/6. So the examples we saw in the previous slides are actually all tight or the worst examples for median treatment estimation in the binary situation. So just to sort of just to make it clear what it means, we have to first show a hard distribution, like we had eta and kappa, for showing the width lower bound, which means generalizing kappa and eta for k-array values. And actually here, I mean, something cool happens. We were able to use a lemma from the work of Prop and Wilson. So it turned out to be slightly trickier than what we were expecting. Because for k-array outcomes, it's not as easy as just thinking about the intersections of ones and ones. And you also need to show an approximation algorithm which can achieve this width. So we showed that as well. So which basically means you have to generalize this notion of rho hat A intersection into something else, because that won't make sense in the k-array version. And it turns out that the algorithm is actually instance optimal, meaning that it's not only in the worst case it's correct, but for amongst all correct algorithms, if you assume that your data is being generated IID from an unknown joint distribution, this algorithm, which generalizes the rho hat A intersection B idea, that would actually be the best one even when you restrict your inputs to be of this form. Right? So it's instance optimal in that setting. So these are the results that we are able to obtain. And I think I'm probably on time to end the talk as well. Yeah, so there are some further directions that we think are very interesting. So one thing is to bring in covariates with some confidence parameter. That is, typically when covariates are used, people sort of just assume a linear relationship with some Gaussian noise. But of late, there has been this line of work started by Dan Spielman and other people in his group, where they are actually saying that suppose you only have 70% confidence in your covariates. Now, how should you design your randomized control trial? And it turns out to be intimately related to discrepancy minimization. And so they were able to sort of match a very TCS-like idea to causal inference. So we would be interested in doing that for the median estimation problem. And well, okay, since you cannot compute the median precisely, are there some other reasonable assumptions on the data which happen in like the real world, where median estimation is kind of easier, right? It's not as tough as without any assumptions. And the third thing which is really interesting according to me is bringing in interference. So imagine that this drug was actually a vaccine. Even though you get control, like you did not get the vaccine, but if your neighbors got the vaccine, you implicitly feel the positive effects of the vaccine. So this is called interference, where the treatment given to I actually influences the treatment value of a different individual J. So under this model, how can we do median estimation? I think that's an interesting question. And that's it. Thank you.
Questions? So in a 2x2 case, it seems to just want to know the full real numbers in 2x2 probability matrix. Right? By knowing marginals, you already know 2, and they sum up to be 1, so that there are only 3 degrees of freedom. So you only want to estimate one thing, which is like the difference of each column or each row.
Yes.
Why don't you just estimate that thing directly instead of like pursuing median, which is like seems like just a function of that. How do you estimate? What do you mean estimate? How do you estimate that thing? No, you cannot, but you can estimate median as well, because median is a function of that.
Yeah, so we essentially go over all possible values of that thing, and we figure out how much the median fluctuates.
Yeah, but I'm trying to understand why people care the median in the first place.
No, so imagine a k-array situation. There the number of the degrees of freedoms will grow quadratically in k. Imagine a KRE situation.
Yeah.
The degree of freedoms would be k squared or order k squared. But,
Uh,
and the median is something else, right? The
Median basically means like I don't care if both treatment and control has no effect or both have effect.
Sorry?
By caring about median, basically say that I don't care about the difference between both treatment and control has effect or has no effect. I think they are the same to me, so that's the only motivation for me to think about median is a meaningful measurement.
No, but that's not true in the KRE situation because when you have, say somebody gets a value 1 and somebody gets a value k, and in a different situation somebody gets the
I'm
value
just talking about
1.
2 by 2 case.
So in the 2 by 2 case it is right, everything is characterized by this one quantity. So you can put it in the way you said.
So you are saying like in 2 by 2 case people don't use median, only when they go up they use median.
Yeah, because very seldom, like in the 2 by 2 case, or I don't really know what happens in the 2 by 2 case because the literature usually deals with the full situation. Like in the covariate situation, they actually have a real value treatment effect.
Okay.
So yeah, in the binary situation, it's sort of characterized by this single degree of freedom thing you said. That's correct.
So, do you have any sort of concentration in your results? You stated it as the expectation of the confidence epsilon is say 1/6. Can you prove that actually it is 1/6 almost for almost all with high probability?
So it's 1/6 for all distributions, you mean? Or like?
No.
Almost all samples.
Oh, yeah, that we can also.
No. It's also interesting, but I was asked in your framework fixed sample.
No, the sample I mean sample over S is what I mean by sample.
Yeah.
You're asking about concentration of this thing.
Yes.
Yes, we can show that.
Because it looks like you use something like Chernoff or whatever.
Yeah, we can show that thing.
You can show that. Yeah.
So I wonder, in the case with covariates, you could imagine a world where there are like features, but they affect things in a very hard to predict way, like not linear or anything. But nonetheless, they are, kind of enough they carry somehow enough information. If that were the way the world was, you could imagine grabbing a sample by pick a random person, and then find the most similar person to them in the data, get them too, and then give one of them the A and give one treatment and one. In other words, you could try to pick random pairs that are each close to each other in the hopes that you're kind of estimating, that the twins, it'll be the twins will be close enough together that they would have the same, because there's this unknown, and you wouldn't even need to know what the function is. Like there's some crazy old function from people's features to outputs. You wouldn't even need to know what it is as long as you have the two people that are close enough together would have the same profile.
So
something like
you
that.
are right. This is called the matching design. What you are describing is called the matching design, and they analyze it exactly the way you say. So if you do a matching design and you want to estimate the average treatment effect, you would always do better than the Horowitz-Thompson estimator. But when there is absolutely no linear explanation, you would converge to the Horowitz-Thompson estimator. So it's sort of echoing the thing you said, that if this crazy function is too crazy, like there's just no way to even linearly explain like better than random guessing, then you would essentially end up with the same estimator as the Horowitz-Thompson one. But if there's some linear explanation between the covariates, then that variance happens to be better than the average treatment effect, as than the Horowitz-Thompson estimator. So yeah, maybe something like that can be also done to the median situation.